Welcome back to Simplifying Synthesis. In this video, we are going to look at the total synthesis and late-stage CH oxidations of ent-Trachylobane natural products. In the previous video, we looked at the retrosynthesis and the cyclase phase of this work, which was concerned with the construction of the carbon framework of the molecule. In this video, we are going to look at the oxidase phase. In this phase of the work, the researchers explored different methods of functionalizing the framework and synthesizing multiple natural products from a small number of intermediates synthesized in the cyclase phase. The first oxidation they carried out utilized methyl trifluoromethyl dioxirane. This reacted selectively with the C11 position, abstracting a hydrogen radical and then forming the carbon-oxygen bond in a mechanism that resembles the oxygen rebound mechanism seen in iron-based enzymes. Further oxidation yielded the product as a single isomer in a 43% yield. There are several factors that we can use to rationalize the selectivity of this oxidation for the C11 position. The first is electronic deactivation from the electron-withdrawing ester group. This reduces the reactivity of the positions close to it and favours oxidation of the most distal ring. Another factor is the relief of diaxial strain. The hydrogen occupying the axial position on the C11 carbon has unfavourable 1,3 diaxial interactions with two other positions within the ring. Oxidizing this position relieves the strain and stabilizes the molecule. A third factor that we can consider is distortion acceleration. This effect arises from the heavy substitution of the ring, which distorts its conformation away from the more stable chair conformation. This distortion favours a conformation which more closely resembles the transition state, and therefore lowers the energy of activation needed for the transformation to occur. This is similar to the entactic state model, often used in bioinorganic chemistry to explain the reactivity of certain metalloenzymes. The next oxidation that they investigated was an electrochemical oxidation using a method that has been widely popularized by Baran, who has used this chemistry to great effect. This reaction uses quinculadine, which is oxidized at the anode, in this case comprised of reticulated vitreous carbon foam, and this species can then abstract a hydrogen radical, again from the C11 position as we saw previously. This positively charged species is then reduced at the nickel cathode to liberate hydrogen gas upon reaction with hexafluoroisopropanol. The radical that is produced on the C11 position then goes on to react with molecular oxygen to form a peroxy radical species. This then goes on to form the C11 ketone in a 36% yield. In addition to this, they also recovered an enone species in a 10% yield, which hasn't been observed in nature. They have proposed the following mechanism for the formation of this product. They propose that the C11 radical is in equilibrium with an alkene species that is formed from the decomposition of the cyclopropane ring. They calculate that there is only a 1.5 kilocalorie per mole difference between these two species. With this radical now residing on the C16 position, it can react with molecular oxygen, as we saw previously. This forms a peroxy radical intermediate, which is reduced by quinculadine and then protonated. This intermediate can eliminate hydroxide, together with the migration of a carbon-carbon bond to form a carbon-oxygen bond. This hydroxide will then attack the cationic C16 position, forming a hemiacetal, which is in equilibrium with the allylic alcohol. It is this species that can be further oxidized to form an enone and generate the product. They then experimented with trying this electrochemical oxidation on the molecule that had the methyl ester hydrolyzed to form the carboxylic acid. In this reaction, only one product was recovered, in a 29% yield, with exclusive oxidation at the C11 position. This highlights the susceptibility of the C11 position to be oxidized, in preference to the other positions. The next oxidation they investigated utilized a Ruthenium-Porphyrin complex. This reaction produced a ketone at the C11 position as expected, and also the partially oxidized molecule possessing an alcohol at this position. The catalyst for this oxidation features a heavily substituted porphyrin coordinating a ruthenium which bears an axial carbon monoxide ligand. This is oxidized by dichloropyridine N oxide to form a ruthenium-4 oxide species. This compound can be further oxidized by another equivalent of dichloropyridine N oxide to form a ruthenium-6 dioxide complex, still coordinated by the cyclic porphyrin. It is this species that reacts with the substrate, oxidizing it to an alcohol to regenerate the ruthenium-4 species. Further reaction can oxidize this further to form the ketone at the C11 position. It is interesting to note that mechanistic studies into this reaction have noted the importance of the purity of the solvent used for the reaction, as many commercially sourced solvents contain trace amounts of cyclohexene as a stabilizer. They found that the presence of this stabilizer inhibits the formation of the active catalyst, leading to longer reaction times. In the next reaction, they used the carboxylic acid and reacted it with White's catalyst. This formed a rather unusual product, incorporating a trifluoroethyl group in addition to a hydroxyl group. This was formed in a 30% yield, and the structure was proven by X-ray crystallography. The catalyst used is similar to that which was used in the total synthesis of deoxoapatine, which we saw in a previous video. It incorporates a bis-pyrrole ligand, which is rigid and helps stabilize the complex. The steric hindrance of the ligand blocks the trajectory that the substrate can approach from, and this improves the stereoselectivity of the reaction. This catalyst first reacts with hydrogen peroxide and triflic acid, which displaces the acetonitrile ligands, forming a manganese oxide, together with the triflate ligand. This reacts with the substrate to abstract a hydrogen radical, reducing the oxide to a hydroxide group and leaving the radical on the C15 position of the substrate. A carbon-carbon bond of the cyclopropane ring can then undergo homolytic cleavage, breaking the bond and combining with the radical on the C15 position to form an alkene. This molecule then reacts with hydrogen peroxide, and the double bond is activated by triflic acid and then reacts with a trifluoroethanol solvent. The researchers now turn their attention to investigating the oxidation chemistry of the compound incorporating a hydroxyl group instead of the ester. They did this by first carrying out a Suárez oxidation. This reaction uses diacetoxyiodo-benzene, iodine, and UV light and produced a product where the alcohol had been oxidized to an aldehyde in addition to the iodination of the C20 position. The proposed mechanism for this reaction involves the formation of a radical on the hydroxyl group, and this undergoes a 1,6 hydrogen transfer to produce a radical on the methyl group on the same face of the ring. This reacts with the iodine to form the carbon-iodine bond. In addition to this reactivity, the diacetoxyiodo-benzene also acts as an oxidizing agent, where it is first attacked by the hydroxyl group, eliminating acetate, which then acts as a base to deprotonate the activated species to produce the aldehyde. In order to oxidize this hydroxyl group without reacting the C20 position, the group instead used a PCC oxidation. The pyridinium chlorochromate reagent is attacked by the hydroxyl group, forming an anionic intermediate, which then eliminates chloride. This chloride can then act as a base to deprotonate the carbon bonded to the oxygen and produce the aldehyde in a 99% yield. With this aldehyde in place, the authors could then explore the final oxidation method, which was a Schönecker oxidation. This oxidation is a directed method which uses a dinitrogen ligand to guide the active catalyst towards the target reaction site. Reacting the aldehyde with 2-picolylamine and tosylic acid as a catalyst produces a Schiff base. This species is then reacted with copper nitrate and hydrogen peroxide. This forms the product with a hydroxyl group on the C3 position, adjacent to the carbon bearing the aldehyde. This was then acetylated with acetic anhydride and DMAP to deliver the final Trachylobane natural product in a 32% yield over 2 steps. The copper complex formed in this reaction reacts with hydrogen peroxide to form an oxygen-bridged dimer with the copper in the +2 oxidation state. This species can reductively cleave the oxygen-oxygen bond together with the oxidation to copper 3. This highly electron-deficient species can then abstract a proton from the C3 position and form a carbon-oxygen bond, which produces the target alcohol along with the starting aldehyde. And with that oxidation, it brings us to the end of the synthesis, which was successful in synthesizing 7 different Trachylobane natural products, in addition to several other useful intermediates that could be used to conduct SAR studies and investigate the biological activity of these compounds. Well, that's all for this week's episode. If you enjoy these videos, please like and subscribe, and if you have anything you'd like to see, let me know in the comments down below. In the next video, we will be looking at an enantioselective formal synthesis of aflatoxin B2.